Welcome to the latest episode of the MFG Radio Network's Lunch and Learn, as we highlight some of the latest advances in manufacturing and design, gain insights about the newest products and technologies to move your manufacturing ahead of the competition. Hello, and welcome to our next Manufacturing Lunch and Learn at GIE Media. I'm Jake Kaufman, a managing editor for the manufacturing group at GIE. We are joined by Aerotech now as they will discuss cylindrical laser processing of medical devices. Now, Aerotech in Pittsburgh, Pennsylvania designs and manufactures best-in-class motion control and precision positioning systems for industry, government, science, and research institutions. Aerotech's precision motion control products provide the critical performance for today's demanding applications in markets such as medical device and life sciences, semiconductor and flat panel, photonics, automotive, data storage, laser processing, military aerospace, electronics manufacturing, test, assembly, research, and development, and other markets requiring high precision, high throughput motion solutions. Aerotech's philosophy of building superior motion control systems starts with designing and manufacturing technically superior products and components. An Aerotech system begins with Aerotech motion components that are already best in class and specifically or specially designed and optimized for the highest performance and lowest cost of ownership available. So today's presenter is Travis Snyder. Travis is Aerotech's Business Development Manager for advanced manufacturing market segments, including electronics manufacturing, laser processing, medical technology, data storage, and precision manufacturing. He has 13 plus years of experience in precision automation and robotics, holding roles in application engineering, field sales, product management, and business development. Travis earned his bachelor's degree in mechanical engineering from Milwaukee School of Engineering. His expertise and passion for innovation make him an invaluable resource for partners seeking to push boundaries in precision automation and in advanced manufacturing. So let's get right to it then, Travis. You can take it away.
Hello, and thank you for attending this presentation. My name is Travis Schneider. I'm a business development manager with Aerotech. I have a formal education in mechanical engineering and have spent my entire professional career in the automation industry, focusing in on applications in the robotics and precision motion control domain. Today, I put together a presentation to provide basically a brief overview of some key considerations to optimize your machine's design when machining cylindrical medical products via laser processes. Much of this content is geared at either manufacturing or engineering teams who are involved in machine design, specification, or the procurement process to equip you with a couple of attributes to keep in mind when either developing your next machine or perhaps refining a machine you already have in-house. I know that these concepts can be broadly applied to other precision machining applications as well, but for the purposes of this presentation, we'll talk to some specific examples within the medical industry. Now, this presentation is going to be extremely brief, so should you have specific applications in mind or would like to connect, I've also listed my email on this intro slide. Jumping right in here, first I'd like to talk to the types of cylindrical products that are commonly made with this type of equipment. Classically, if we think about tubular products, we think about stents of all types, ranging from cardiovascular to neurovascular. But there's a variety of other medical devices that people create as well from cylindrical or tubular stock, including things like valve frames, grafts, hypotubes, and other various forms of surgical instruments that might be used for minimally invasive procedures. Now, the diameter of these tubes can range from fractions of a millimeter to tens of millimeters, with the total part length ranging from the millimeter range to meters. And often these machines are using femtosecond or fiber lasers to cut these parts. Before addressing aspects of the machine, first I wanted to talk about the objectives that we're looking for as it pertains to the parts being manufactured. Particularly within the medical industry, quality comes to mind first, especially given the types of products and uses for those products. Quality must be front of mind. We want to ensure that we're producing parts consistently that lack defects to ensure both patient safety and efficacy, so avoiding hazards to the patient and potential recalls. Producing parts generally requires a quality machine and that has to be designed with intention. That can't be by accident that happens. Beyond quality, throughput is often the next topic that comes to mind. Generally speaking, you want to produce as many quality parts as possible with as few machines as possible to improve upon your cost performance. And then assuming we've met our quality and throughput metrics, we'll then also want to maximize our material efficiency or minimize material waste. So as I talk through this presentation, I'm basically going to break down these topics into a couple of foundational elements of a typical machine's design. First, I'll talk through traditional machine design elements, primarily from a mechanical standpoint. Then I'll talk through some control functions that enable optimal throughput and quality, and wrap up with some laser control features to also bear in mind. When we talk about the objectives for these types of machines, often we're talking about minimizing potential sources of error. These error sources can come from a variety of different areas, but for the purposes of this presentation, I'll often refer to them in one of three categories. First is unobservable error. Now, as far as motion control is concerned, often we use a variety of different sensors to detect in order to mitigate this error wherever possible. Examples might include things like encoders or temperature probes to kind of keep our machine in check. When we talk about unobservable error, we're talking about things that we can't detect or that we don't have sensing to account for. Often these come from machine frame elements or the part itself, either bending, twisting, or vibrating at a microscopic level. These types of errors can result in the motion system thinking it's doing everything perfectly when reality is something different. Second is tracking error. Often when we're using various elements of motion control to guide the part in relation to the tool, with limited dynamics, this isn't necessarily an issue, but the faster we try to drive the system to achieve those higher throughputs, you might end up seeing following errors or tracking errors as the machine approaches these limits where the tool is basically struggling to achieve the desired profile of the part. And then last is processing errors. As mentioned earlier in the introduction, often these parts are being manufactured through a laser cutting process. If the output of the laser isn't well synchronized to the part, it might generate undesirable features due to poor laser material interaction, which can also result in poor quality or waste. With that, let's examine some machine design elements. Now, under machine design, the first concept I wanted to address is stiffness. Now, if there's a takeaway here, it's that everything is basically a spring and nothing is perfectly rigid. That is to say that any machine element will bend or vibrate to some degree, but the goal should be to minimize those deflecting elements where possible, especially if those elements might impact part performance, thus minimizing the unobservable errors or tracking errors as a result. Equally important on the positive side, the more stiff a machine structure, the more responsive the machine is. When a machine structure is more stiff, it focuses or directs more of the energy from the motion control components toward their intended target as compared to being lost in bending elements of the machine. This results in a more responsive machine with higher dynamic capacity, enabling higher levels of throughput. Now, fundamental mechanics tells us that if we're to put a series of springs in a line with one another or elongate a given spring, we arrive at a less stiff system. The longer these series of springs, the longer the path a force has to travel to get back to ground to basically dissipate energy throughout the machine frame. However, if we're able to shorten the length of these springs or place multiple springs in parallel with one another, we're able to increase the stiffness of the system. And consequently, this also provides multiple paths for that energy to be dissipated back to the machine base. It's generally well understood that any force being applied or imparted by the machine will have an equal and opposite reaction force that needs to be accounted for within the machine structure. These reaction forces need to translate back to ground somehow, so the longer loop we create, the greater impact on the machine's performance. However, if we're able to provide multiple paths or shorter paths for this energy to be translated back to ground, the more stiff the system. This is illustrated in the following series of structures illustrated on this slide here. First on the left is an example of an open loop structure with those machine elements acting as springs in series. But then as we look towards the two machine examples in the center and then the one on the right, we see a closed loop structure that makes use of a bridge design, allowing for multiple paths for that energy to be rejected. Furthermore, you can see how the tube processing system on the far right, we're using a much more stout structure with wider elements to further improve the stiffness of this machine. As a result, this system will have improved performance in terms of the precision as compared to the other structures, all other things being equal, as it'll be able to manage more aggressive moves and allow for more injected inertial energy per unit deflection between the work point and the part. Now, in the case of processing of relatively small medical tubing, we're also concerned with the supporting of the part. In general, tube stock should be supported as much as possible to mitigate those unobservable errors that might exhibit themselves into the part structure itself. With a tubular part, we're generally concerned with two types of induced errors. First being runout, which is the radial wobbling or whipping motion of the tube as it's accelerated in a rotational fashion, where there'll be a natural tendency for that part to kind of wiggle if unsupported. Second is the windup of the tube due to those significant rotational accelerations that might create rotational deflections in the tube itself. Now, proper bushing design can help to mitigate either of these scenarios. However, there's often a balance to be struck here between basically the amount of bushing material versus the amount of exposed part. The more bushing material you use, often the more friction you introduce into the system, but the less bushing material, the less support of the part. So obviously there's a balance to be struck here in order to minimize material waste, but also adequately support the part. The next topic we'll cover is machine control. The first fundamental principle that I wanted to raise awareness of is impulse forces and discontinuities of motion. So impulse forces come up when we're talking about really sharp, instantaneous commands where the machine is driven to accelerate or decelerate basically on a dime. One might think of a step function with a very narrow width as being a prime example of this. This is illustrated in the graphic on the left with the red line having the sharp increase and decrease in force per unit time. This sort of impulse force injects force over a large spectrum of frequencies into the machine. Often in the case, we're stretching into the kilohertz range. The problem here is that the control system typically can only respond to frequencies as high as, say, like 300 hertz or so. This means that excess energy that extends beyond that range is going to be wasted energy that the machine will need to absorb and reject back into the ground. However, if we're able to soften the trajectory of that acceleration profile closer to that of the blue curve, you can see a significant decrease in the amount of energy needing to be rejected. That is the area under the curve, the difference between the red line versus the blue line on the right at those higher frequencies. So if we're able to create broader acceleration profiles, often we'll have less energy that needs to be rejected or dissipated. So this might be obvious in the previous example, but when we look at a common stent profile as what's depicted on the screen here, you can see where examples of these discontinuities might come up. Highlighted first in the green circle is an example of some nice swooping curves that allow for more gentle accelerations and decelerations. However, highlighted in the red circles are some sharp points where a straight line meets a radius feature carved within the stent structure itself. Now, this abrupt change in direction to the motion control system will generate discontinuities of motion and those impulse forces that we're trying to avoid. So what can we do instead? Well, basically, there's three options to consider. First, and the most simple, is to avoid these sorts of sharp features within the design of the product. But if that isn't an option, there are other options to also be considered. Second is you can insert Bezier curves into the motion profile, or basically, as you see illustrated here, the laser, while it's cutting the blue section, the motion system will generate these yellow loops where it arrives at the part to be cut from a different angle in order to avoid those sharp turns. This generally creates a longer distance that the motion system needs to travel in order to execute that profile, where the blue is where the laser is obviously activated, and basically the yellow is wasted motion to loop the motion system around and then come back into the part profile. So it's going to have a negative impact in terms of overall throughput, but will allow you to avoid those discontinuities. The third option, if you're looking to avoid those Bezier curves, is to basically take advantage of a function that's known as look ahead. And this is available in most modern motion control products. With the look ahead feature, basically the motion control system is aware of future motion commands coming up, and it basically attempts to compensate for them by backing off on the acceleration profiles to achieve a more desirable path profile. So this is going to obviously slow the acceleration and might result in some rounding of some of these features by applying a small radius, as you see here. But know that these radii are often configurable within the motion controller such that you can apply a certain bound to which, the motion controller can kind of soften those edges from the targeted path. Now, deviations from the targeted path are often referred to as tracking error. In the previous example, we were intentionally allowing the motion controller to make these minor adjustments on our behalf. However, in some cases, there are situations where the commanded motion basically exceeds the capability or the bandwidth of the motion system to execute a given trajectory. This happens most regularly when we're trying to bump up accelerations to improve upon throughput. When the bandwidth of the command signal exceeds that of our motion system's capability, it's going to result in some degree of error. This resulting error is what we refer to as tracking error. Looking at another basic example here, we have a commanded move requiring some XY motion to generate a curve. Now, on the left-hand side, you're seeing without that look-ahead function enabled, you can see where we're driving the system beyond what it's capable of, and it attempts to accelerate through that curve, generating some error depicted by the red dotted line. Now, with the look-ahead function enabled, the motion controller is able to peer into these upcoming commands and then appropriately throttle our acceleration in order to minimize this tracking error deviation from, say, 10 to 15 microns on the left with the red line to a single micron on the right with the green line. Now, this does mean that for the curve section, that we will complete that section of the motion profile slower. However, if we're to look at the entirety of the profile, it is likely that we'll be able to achieve the entire profile faster with this function enabled, as we won't be bound to a single acceleration limit to accommodate for just the acceptable tracing of this particular section of the curve. So we'll be able to accelerate faster into those kind of straight line sections. Finally, let's talk about some laser control functions. So just as important is understanding the nuance associated with the motion control commands that allow for speeding up or slowing down to achieve the desired paths to be completed, we also want to pay close attention to the interplay between the laser and the part. Here again, with more modern motion controllers, you can take advantage of several functions that allow you to tailor the output of the beam in relation to the part in a more coordinated fashion. First is a function that allows the beam to maintain a constant average fluence output from the beam to the part. As you might imagine, if the beam was left at a constant power while the part was sped up or slowed down under it, the regions where we would be moving faster or the part faster, you might see more limited beam power imparted into the part as compared to regions where the part was slowed down might have increasing levels of laser energy imparted onto it. By allowing the motion controller to coordinate not only the motion of the part, but also the powering up and powering down of the beam in relation to this, we're able to arrive at a more consistently made part. Similarly, there are additional functions that allow for us to vary the beam output relative to position. This is a bit more unique function, but it also is highly valuable as it pertains to part quality, as you're able to specify or basically control how much laser energy is deposited throughout the part path based upon encoder position directly. Finally, there are even more advanced control algorithms that allow for tight coordination of motion axes to laser scan heads and laser output in the event that you're taking advantage of like a galvanometer, for instance. One of these functions is often referred to as infinite field of view, where we take advantage of the high dynamic range of the laser scan head to direct the beam and coordinate that based upon positional information with the motion axes simultaneously to deliver that beam even faster than what you might be able to otherwise. This concludes today's presentation. Though this was a very brief presentation, I hope it was both informative and well worth your investment of time. Should you want more information on any of these topics, there are a number of white papers and videos available at aerotech.com under our resources section that I would strongly encourage you to check out. Alternatively, if you have any questions, you can always contact me directly via my email address here listed again on the slide. And again, thank you for your time and attention today.
All right. So Travis was nice enough to join us for some Q&A after that presentation. So thank you so much, Travis. Looks like we do have a few coming in. So the first question I have to ask you is, how can I elevate the throughput performance of a prospective machine design relative to another prior to building it?
Gotcha. Thanks for that, Jake. You can hear me all right, right?
Correct. Yes.
Awesome. Yeah, so that's a good question. So I think the question is basically how can I evaluate the prospective performance of my machine prior to putting it together? Well, this is something that comes up quite regularly when we're talking about a project, particularly on the front end of a project. And as you might imagine from the presentation materials, it's somewhat of a multifaceted question to answer. So the short answer I would give is that it comes with a degree of experience and insight into a given application in order to truly answer that question. But I'll try my best to round it out in a couple different topic areas here and now. First of which is there's a variety of different simulation tools that are used within the automation and robotics space where you can evaluate the motion of various components in real time and get analytic analysis of their relative performance to one another. But the one thing I would caution people against in that regard is that only gives part of the story. There's an underlying assumption there that the part itself can keep up with the dynamics of the machine. So you also need to take into account, the material that's being cut, what kind of structural elements still exist within the material. Is it going to start to wobble or run out, as indicated earlier in my presentation? And then another non-trivial element to also bear in mind too is the laser to part interaction. There'll be certain limiting factors between the ability of the laser to adequately cut the material such that we're not encountering excess dross or whatnot when cutting a part. So clearly everyone always wants to crank their machine up to 10 and go as fast as possible. But sometimes there's these elements that have to be taken into account in order to kind of clear the path. So again, this comes with experience, but luckily, Aerotech has 30 years of experience in helping manufacturers produce systems that laser cut medical devices, and we have 50 years of experience in motion control. So we have a very esteemed team of applications engineers that help people to sort through these types of details.
Awesome. Thank you, Travis. So it looks like there are a few more questions. So are there ways as a design engineer to evaluate a given device's profile to find the trouble areas automatically?
Yeah. So as a matter of fact, we have a number of different software tools available within our suite that basically enable a user to input a given part profile, and then it automatically will highlight those problem areas or trouble areas. So here again, the software will highlight the regions of the part that are under the greatest demand from a dynamic performance standpoint. But here again, this is applying some assumptions around that being just based upon the motion system. You also have to take into account stiffness of the material and some of the laser material interaction as well.
Awesome. Thank you, Travis. And it looks like we do have one final question. What advice would you give a device manufacturer when evaluating different machine suppliers?
That's a good question. So a hard one to quantify or provide direct firm guidance against, but I'll give this a shot. So to me, for something as important as like a medical device, in my opinion, you're going to want to work with someone who truly understands your needs and the details of the application. And equally as important, be there after the machine is sold to support it in the field. Clearly, there's, given the nature of the types of devices that we're talking about and the equipment at hand, there's an element of technical competence that's required. But in my experience, I almost feel that the support element is equally as important. So if it were me and I was a medical device manufacturer and I was thinking about what's most important to me, I would try to think real hard about your objectives for your machine and what you're seeking to achieve. I would also try to articulate that as best you can to a supplier. Oftentimes, I feel like there's some degree of like reluctance in conversation for fear of like getting taken advantage of in a given situation. But I think it's real important to be as transparent as possible with what you're seeking to achieve in order to maximize that supplier's ability to support you with their resources. But if you feel like you're getting very vanilla answers and aren't necessarily being listened to, I think that's generally a sign that you might want to look elsewhere. And then similarly, I would have real pointed questions about a supplier's aftermarket support to make sure that they're able to reach you wherever your manufacturing locations might be and provide you optimum support levels throughout the life cycle of your product.
Awesome. Thank you, Travis. And thank you once again to Aerotech. They're located in Pittsburgh, Pennsylvania, and design and manufacture best-in-class motion control and precision positioning systems for industry, government, science, and research institutions. Aerotech's precision motion control products provide the critical performance for today's demanding applications in markets such as medical device and life sciences, semiconductor and flat panel, photonics, automotive, data storage, laser processing, military aerospace, electronics manufacturing, test, assembly, research and development, and other markets requiring high precision, high throughput motion solutions. So Travis, thank you once again for the delightful presentation today, and I hope you have a wonderful day.
Sure. Thank you. Take care.
You can find more Lunch and Learns, plus the MFG Radio Network's other podcasts on Apple Music, Spotify, Google Podcasts, or on our websites at todaysmedicaldevelopments.com, aerospace manufacturing and design.com, and evdesignandmanufacturing.com.